All right, so the final homework. Let's see what we're going to do. We've got basically three media, which is air here. And then did I call this quartz? And then I have a liquid over here. The quartz had a index of refraction of 1.6. The liquid had 1.2. And air, of course, has 1. So what we want to do here is we want to just figure out how the I forgot to take that off anyways, how the light ray moves through here. And this is all just going to be through Snell's law. And we want to figure out more or less what these angles are. Now remember, these angles are with respect to the normal. So this is coming in at 60 degrees. It's going to come out here, so this is going to be theta 2. And then this guy here, the normal, the perpendicular to the interface, this will be theta 3. All right, so that's how we're going to do this guy. So this guy comes in and it refracts and then refracts again, and it refracts inward and then outward a little bit because it refracts inward when you have the higher index of refraction when it slows down. Then when it speeds up, right, you have a lower index of refraction, it increases that angle again. So let's just look at this first one. So what we want to do here is we want to find theta 2. So we want to find sine of theta 2. And that's going to be equal to the n1 sine theta, 1, right, divided by this n2. So we want to get this n2 off of that guy, so we have to divide. And I think I'm pressing the button accidentally, so it's not writing. So we have sine theta 2 is equal to n1 over n2 sine theta 1. Let's see what we have for n1. n1 in this case, well, n1, so I'm going to call this 1, 2, and 3. So n1 is just going to be 1. n2 is going to be 1.6, and sine of theta 1 is the sine of 60 degrees, right? And that is the square root of 3 over 2. So that's 1.732, I believe, as the square root of 3 over 3.2, which is a little over half, which is 0.5413. And so that's, like I said, sine of theta 2. So to find theta 2, we have to take the arc sine, or sine to the negative 1 on your calculator, probably. It's on my calculator, of 0.5413. And that's going to give us, if you're in degrees, 32.76 degrees. Now, the big problem with these problems, whenever you're doing an arc sine or a sine or something like that, the big problem that students run into is that they have the mode on the calculator wrong. So it will be in radians instead of degrees, or worse, there are some other things that it could be. But just make sure that your calculator is in degrees when you do that. It'll be much, much easier. Okay, so you see that this is almost half the angle. Coming out, it's at almost half the angle from the perpendicular and as it came in. And that's, of course, because this has increased. Now, we want it to enter the fluid as well. So one thing we could do is we could use this angle here, and this angle here. But there's a trick here, and that is, remember, this n2 sine theta 2 is going to be the same. Remember, your angles here, these angles from trigonometry are the same. So we have n2 sine theta 2 coming in here, and that's equal to n3 sine theta 3. I have enough room? I just barely do. And so that means that we can ignore that stuff in the middle, and n1 sine theta 1 is equal to n3 sine theta 3. So sine of theta 3 now is equal to 1 over n3 times sine of theta 1, right? And that's going to be 1 over 1.2 now times the square root of 3 over 2, which is the sine of 60 degrees. Okay, so that's 1.732 over 2.4, which is 0.7217. Okay, is that looking good? And now we do the same thing. We have the sine of theta 3. We want to have theta 3. We want to find the angle. So we have to do theta 3 is the arc sine of 0.7217, which is 46.2 degrees. All right, so it got skinnier here. It got 32.76. Then it got fatter here, 46.2, but not as fat as this one because that's 1, and that was 60 degrees. So that makes sense. That's exactly what we thought would happen. All right. The one other part of this problem that we're looking at is the change in the speed of light. I asked for this in 10 to the 8 meters per second. All right. And remember, c itself, speed of light, is equal to 3 times 10 to the 8 meters per second, which is the reason why I care about that. All right, so the change in the velocity as this thing goes from here to here, it's going to speed up because the index of refraction is smaller, is the difference in those velocities. The velocity of light in a medium is c over the index of refraction. So that's c over n2 minus c over n1, which is 1 over n2 minus 1 over n1 times the speed of light. N2 is what? It's 1.6, or 1.2, excuse me, and the other one is 1.6, so this is smaller than this because it's got a larger number in the denominator. That's 3 times 10 to the 8th meters per second. Now the difference between those two things, if I ask my calculator, is 0.208 times 3 times 10 to the 8 meters per second, and hopefully there's enough room. Okay, I can get at least the equal sign, so probably this is fine. So this is 0.625 times 10 to the 8 meters per second. Okay, so that's how much the light slows down when it enters. And because it slows down, that's why the angle increases. So this was mostly just Snell's law, right? We did Snell's law at the two interfaces. We learned a neat little trick that happens because of some geometry that we learned, I say, but more likely we forgot from high school geometry. Freshman or sophomore year, I don't remember. I'm an old man. And I don't even remember what it's called. That's how old I am. And then we went ahead and we found the speed of light, right? Remembering that the speed of light in a material is dependent on that index of refraction, which is just an index that says how much slowing happens in that material. Okay, so that's our first problem. Our second problem is the fun one with all the fun math that's going to drive you crazy. So in this case, we've got 3 different paths. Path A, I think, is this green one, from this point to this point. Path B is straight and then down, and path C is this straight one. Now, none of these is the least time path. I'd like to say that right now. None of these is the least time path. But they all have some, they all have different times with them. So, we like the least time path for reasons. least time path is actually this red one that I'm drawing here. It's somewhere in between the blue and the green. So now what we want to do is we want to figure these things out. Now, I've said that this is 30 centimeters and this is 90 centimeters, and I basically ended up saying that each one of these is the same size. Now, I think the way I programmed this was that this is true for you as well. It was for all of the ones I looked at, and I probably should have just looked in the code. It's been a long time since I programmed it, but I should have just looked in the code to see what it is. So basically the way we're going to look at this is we're going to say, okay, we're going through this air, then this medium with an index of refraction of 1.5, which is a fairly common sort of level for a medium. Then we come back out into air again. So we want to add up those times. So the total time in each one of those three regions, 1, 2, and 3, is the time for the path. So basically all we have to do is a lot of kinematic stuff, right? We're going to have v is equal to the distance in the material over the time. So the time is equal to the distance over the speed. The speed now, this is 1.5, so the speed itself is going to be equal to 3 times 10 to the 8th meters per second in these two parts here on either end. But for the central part, we have to divide by the index of refraction, which is 1.5, so that's 2 times 10 to the 8th meters per second. So we're not going to have to calculate these over and over. We already know what they are, right? We're just going to deal with it. Okay, so our first deal here is this one. And for this one, the light beam goes through the same distance in each material for the green one. So we should just figure out what that distance is, right? And that 3 times that distance from here to here is equal to 1 factor here. So that's the square root of 1 squared plus 3 factors here. So 3 squared times 30 centimeters, which is 0.3 meters, which is equal to the square root of 10 times 0.3 meters. If I divide by 3, that's equal to 1 over the square root of 10 meters. I ran out of space, so that's 0.3162 meters, so a little under a third of a meter. So that's what we're going to use here, right? Remember, this is 3 factors, 1, 2, 3, that's why it's 3D here. And the D we want is just the distance in each one of these media, because we're going to add them up, the times for each one. Now T1 is equal to T3, which is equal to D over C, right? This distance here and this distance here, which are the same distance, over the speed of light itself in air, or in vacuum really. So that's 3 times 10 to the 8th meters per second over 0.3. Or got that backwards. 0.3162 meters over 3 times 10 to the 8th meters per second. So that is 0.10. 15 is 5. That leaves me 1, 2, 4. 0.1054 times 10 to the minus 8 seconds, which is equal to 1.054 nanoseconds. So that's part 1 and 3. So we've got 1 and we've got 3. So we need to find, that's t2. Here we have the same distance, right? We are going to divide by the velocity of light in the medium. So then we have 0.3162 meters over 2 times 10 to the 8th meters per second, which is really just equal to 1.5 times that. Which is 1.581 nanoseconds, right? 5 times. So that's 1.0 stuff. This is 1.5 stuff, right? So it's about right. Should be over 0.75. It is just a little bit over 0.75. So we're good with that. So the total time here is 2 times this 1.045 nanoseconds plus this 1.581 nanoseconds, which is 3.6 9 nanoseconds. All right, so we've got 3.6, 3.7 nanoseconds for this straight line. Now for the longer one, that will, oh, yeah, got an error there. For the longer one here, we've got these two distances are the same and this one is longer. Because this distance and this distance are the same, that's longer by this factor of the square root of 2. So this should be fairly simple, right? So t1 in this case is this distance here, right? So that's that distance over c. It's a different distance. It's 0.3 meters. And it's divided by 3 times 10 to the 8 meters per second because it's in air, right? Part 1 is in air, part 2 is in quartz, and part 3 is in air. So that's 1. I'm going to bet that's 1 nanosecond from all the stuff we did previously. So a lot faster through there. T2, we just said that the difference between these two is a factor of 1.5, right? So this is 0.3 meters over 2 times 10 to the 8 meters per second. So 3 over 2 is 1.5, so it's 1.5 nanoseconds. And the tough one is T3, which has the square root of 2 times the distance over c. Well, that's the square root of 2 times d over c. We already know what d over c is. That's 1 nanosecond. So that's 1.414 nanoseconds. Probably you don't have to care about that. It's going to be much larger than the other two. So t is going to be equal to 1 nanosecond plus 1.5 nanoseconds plus 1.414 nanoseconds, which is equal to 3.914 nanoseconds, or 3.9. It's the longest of the three. And then the last path, I'm going to have to write over these other ones just for space because there's not a lot of space left. In this one, we have T1 and T3 equal to each other again. In this case, their distance, let's call it L, is equal to the square root of 1 squared plus 1/2. So this is half of that 30. 1/2 squared times 0.3 meters, right, which is going to be equal to let's see, the square root of 5/4 times 0.3 meters, which is 0. This has to be done with the calculator. Well, it doesn't have to be done with the calculator. I don't know. Do they still force you to learn how to do square roots by hand? That was an awful, awful experience. So I hope they don't. I hope they don't. I hope they didn't do that to you. That was really just awful. I mean, it was a procedure, you could do it, but it didn't really explain anything about square roots other than you want to use your calculator. All right, so that's our L, so that'll be true for 1 and 3. For 2, we just have this distance 0.3 meters again. So now we have T1 is equal to T3 is equal to L over C, which is 0.3354 meters over 3 times 10 to the 8 meters per second, which will be 3 divided by 3 is 1.3 divided by 3 is 1 divided by, or 5 divided by 3 is 1, right? But now we have 24. 24 divided by 3 is 8 nanoseconds. And then T2 is just this guy right here. Right? We've already done that. So that's 1.5 nanoseconds. So T in this case is 2 times 1.118 nanoseconds plus 1.5 nanoseconds, which is 2.236 plus 1.5, so that's 3.736 nanoseconds. All right, so that is how to calculate those times, right? And we find that this is about 3.7, the straight line, and the broken line here is about 3.7. It's reasonably larger in this case, but it's still like that. So somewhere around here should be the minimum, right? So the minimum is either on this side or that side, but probably over here, since this other yellow one is almost 0.2 nanoseconds larger than the blue path. So probably something like this is the actual path, where there's something in the middle there. Actually showing that is a major hassle. And if I really wanted to hassle you, I could show you, right? I could have done the actual path. And actually that's a good idea, but maybe for another class. All right, so that's least path stuff, least time stuff. That's, remember, Fermat's principle, which gives us refraction and actually gives us the least time path. It's something very important. It's something that we really care about a lot in physics that we don't really get to in lower level classes. So that's a special sort of secret that I gave you in this class. They don't want you to know that if you're not going to take differential equations. All right. And I don't know why they don't want you to know that, but they do. All right, so the third question is just basically calculating speeds of light and then seeing if you had a similar situation in mechanics, what would happen. So the part C is an analogy, and the analogy is, well, if you've got a box sliding along here, it's going at 3 meters per second. It comes up here, it goes up some height h, and it reduces its speed, and it'll reduce its speed proportionately as what happens here. Then what is that height going to be, right there? So we'd have to figure out what this speed up here is first, and so forth, so that it matches the speed reduction. And I should have used a different number here. I should have used a number that's going to match the faster of these two speeds, which we'll find in just a second, right? Actually, it should have been 2 meters per second, then it would have been a lot easier. So I kind of screwed this up a little bit. It's not a real screw up, but it could have been a more direct analogy, at least numerically. All right, so let's find the speed of light in the first material. Well, remember v is equal to c over n. So we have 3 times 10 to the 8 meters per second over 1.5, which is the index of refraction, which is just 2 times 10 to the 8 meters per second. Like I said, this would have been better as a 2. The speed of light in the second material, well, again, we do v equals c over n. C remains 3 times 10 to the 8 meters per second. We have an index of refraction of 2, so that's a 1.5 times 10 to the 8 meters per second as our speed of light in the second material. We've done a couple of these already, so it should not come as a surprise. Calculating the speed of light in a material is not super difficult if you know the index of refraction. And now again we come to our analogy. Right. Again, we have our box. It's going at a speed of 3 meters per second. It comes back up here. It's going at a lower speed, and we'll have to calculate that. So the initial speed is 3 meters per second, and the final speed is going to be a reduction similar to this reduction. So we're going to start with 3 meters per second and reduce it by the ratio of 1.5 to 2. Right, so that's going to be 1.5 times 1.5, which is 2.25 meters per second. So that's a reduction, 2.25 meters per second. So we want to figure out how high this bump would have to be to make that reduction in the speed. Okay, so we have to use conservation of energy. Remember that's K1 plus U1 is equal to K2 plus U2. We're going to count our initial height as 0, which means there will be no gravitational potential energy. So you'll remember then that we just have the kinetic energy, 1/2 mv squared. That's going to be equal to the kinetic energy afterwards, which is with the new speed, 1/2 mu squared, plus the gravitational potential energy here, which is mgh. Right? So there, the first thing we can do is we can cancel out these m's, right? Then we can multiply everything by 2, which gets rid of these, right? So now we have something we could actually solve for h with, right? So this is equal to v squared. So v squared on this side, v squared on that side. So we've got that. So I guess the first thing we do is we subtract u from both sides, u squared from both sides. So we have gh is equal to v squared minus u squared. G is, what did I use? I used 9.8 meters per second squared. H is just h, and v squared is 3 meters per second squared minus the 2.25 meters per second squared. All right. So we divide by the 9.8. So we have h is equal to 9 meters squared per second squared minus 2.25 squared, which is really awful, 5.06. That's close enough for me. Meters squared per second squared over 9.8 meters per second squared. So that's an acceleration. These are velocity squares, so meters are going to be left, so we're good. I guess our first thing here is to subtract, so that's a little less than 4. That's 3.94 over 9.8 meters. And actually, oops, I forgot the 2, didn't I? There was a 2gh. There's a 2 here, so that's 19.6. Okay, so That gives us a 0.201 meters. I think I asked for it in meters, but it's 20.1 centimeters if you're keeping track at home. So that's how to do this. Parts A and B are sort of simple. Part C, you have to go all the way back to Physics 1 to remember how to use it, but it's a pretty reasonable thing to look at. All right, and the last one. Okay, this is the interference one, basically. So we're going to look at basically what happens with this laser light. So we want to figure out the energy of a single photon. Remember the E equals HF thing. Although we know this in wavelength, right? So we're going to have to figure out what the actual frequency is. Then we want to find some, double slit experiment thing here. So we have our double slit experiment, and we want to look at the spacing in the interference pattern, right? And then finally we'll want to look at a diffraction. We're looking at Bragg diffraction, and we're going to figure out what the lattice spacing is in a nanodot array, in case you're doing a nanodot array. This is something at least they were planning on trying to do for hard drives. I'm not sure where they ended up with. They were doing some discrete track recording. They may be to the nanodots by now. They may not. It's really hard to get a really good pattern of nanodots on a single platter, but it's worth money to them, so they might figure out a way to do it. All right, but we want to go back to this photon first, just figure out how much energy it has. But first we have to figure out its frequency, right? So we have the quantity, or the identity, lambda times f is equal to the velocity. The photon itself is going with c, so it's going to start off with an energy of, or it's going to have a frequency based on this. Let's see, our frequency is therefore c over lambda. C is, as we recall, 3 times 10 to the 8 meters per second. And lambda is 600 nanometers times 10 to the 9 minus 9th meters. It's actually 6 times 10 to the minus 7, right? So we have 1/2 times 10 to the minus, or 10 to the 15th, not the minus 15th, hertz, which is something we're going to call 500 terahertz, which is just about right. Something like 500 terahertz is the frequency of a photon, somewhere in that range. Good thing to remember. Now our energy, that's Planck's constant, 6.626 times 10 to the minus 35, or 4, joule seconds. We're multiplying that by 500 terahertz, or 1/2 of times 10 to the 15th hertz. The hertz is 1 over seconds, so we'll just use that because the seconds cancel out. So and I want to use this formulation because then we just divide this number by 2, right? So that's 3.313 times 34 minus 15, which is times 10 to the minus 19 joules. Okay, and then if it was 10 to the minus 20 joules, it would be 33. If it was 10 to the minus 21 joules, it would be 331. So that's more or less the energy. It's not a lot. I don't even remember what 10 to the minus 21 is anymore. Remember Dan Drexler's book really, really cared about it, and when I taught nanotechnology, maybe it did something as well. But you just don't use that very much. if you're using energies like that, you're probably using electron volts instead. So in that case, we have a completely different numbering system. That makes a little bit more sense. It has a better feel to it than 10 to the minus 21. All right, so part B, we want to look at our double slit experiment. Okay, so our double slit experiment had our screen here, and our screen would show some dots. And these dots are width W apart. The slits are as a width here S. We have some distance here D. And we want to figure out what S is, all right? And basically the way this works is S over the distance, the slit width over the distance is equal to lambda, the wavelength over the interference pattern, interference length, the peak to peak length here. So something about the light is equal to something about the geometry, right? This has to do with the light, this has to do with the geometry, and there's that's sort of an amplification factor, or actually in this case the opposite of an amplification factor. So a reduction factor. So we have S over D is equal to lambda over W, in this case, times D. We said lambda was 600 times 10 to the minus 9 meters. W, the separation here is 5 millimeters, so 5 times 10 to the minus 3 meters, times this distance, which is 100 centimeters. We'll pretend that's 1 meter. All right, so that's 6 over 5, so that's 1.2. Actually, let's call it 120. So 600 over 5 is 120. Then we have, that's because these are both factors of 3, so that gives us times 10 to the minus 6 minus 9 plus 3. And then we have meters, so that's 120 micrometers as the distance between those slits, which is pretty slim, right? That's 1/10 of a millimeter, basically. A little more than 1/10 of a millimeter. Almost 1/8 of a millimeter. Probably not something we'd really look at in the lab, but you could do something like that. When they do the diffraction gratings, they have spacing similar to that. Let's see. That is that one. So we want to do the Bragg thing and figure out the size of the nanodots. So Bragg's law was what? 2a sine theta is equal to, oh, this should be 5 for me. I forgot to edit that. 2a sine theta is equal to lambda. So a is equal to lambda over 2 sine theta. Lambda is 600 times 10 to the minus 9 meters over 2 times the sine of 5 degrees, which is equal to 3 times 10 to the minus 9 meters over the sine of 5 degrees, which is something very small, 0.08716, which ends up being about 3.4 micrometers. Oh, times 2. Oh, it's 10 to the minus 7 because I have those two guys. So that's pretty reasonable. It's actually easy to get dots with that spacing, so that's something really doable. I could have made them closer together, which would have had me do more things. Okay, so in this case, we're just looking at interference phenomena. First, we are figuring out the energy of a photon because we love doing stuff like that. Then we're looking at double slit interference and then some Bragg interference with the same laser. That's sort of the thing that's pulling it all together, I guess. But really, we had a whole lecture on applications, so I wanted a question on applications. And unfortunately, the applications are just equations and plug them in sort of things, which makes me a little bit sad, but not too sad. All right. So there we are. That's the homework. I hope you did really, really well. And if not, give me a call or send me an email or just talk to me. There's still a couple of days where I'll be sitting around at 9:30 waiting for people to talk to me. So if you have questions, just talk to me about stuff and I'll try to help you out. All right. So bye now.